In this lecture, I'm going to talk about hierarchical clustering, which is a form of clustering where we have groups nested inside larger groups. And we're going to look at two different approaches. Agglomerative clustering, which does this nested clustering from the bottom up, starting with individual examples and then grouping them, and divisive clustering, which will do it the other way, starting with a large cluster and then splitting it apart. We're also going to look at clustering features. This is one approach to feature reduction, to dimensionality reduction, that uses clustering algorithms. So let's start with this idea. The idea of hierarchical clustering is to group examples into clusters of similar examples, but then group those clusters into groups of similar clusters and so on. So one example of this would be the tree of life, where we have different species or different taxa in groups that are themselves part of larger groups and larger groups, so we can draw a tree representing all of these relations. We can apply this in many other fields. For example, gene activity patterns may help us distinguish between different species and the relatedness between the species. So we have here examples of different organisms from different species, and we can build this phylogenetic tree from these patterns by clustering these patterns hierarchically. The idea is that these clusters, which are formed of groups of examples and then groups of examples, can be represented easily as trees. For example, here we have B and C, which are together forming one cluster, but then they are part of this larger cluster here, which includes B, C, D, E, and F. And this D and E are also clustered that is part of this intermediate cluster D, E, and F. So to represent these groups here would not be as easy as it is when representing as a dendrogram. So this kind of tree where we can see more easily which groups belong to which larger groups. So to cluster, in any case, we always need to measure some similarity or difference between examples. So we have general terms for this: proximity, similarity, dissimilarity. Distance is a special case of dissimilarity, which meets these constraints. For a distance, it must be positive or non-negative. It must be symmetrical, so the distance between x and y is the same as between y and x, and it fulfills this triangular inequality. So the distance between x and z cannot be greater than the sum of the distances of x to some y and then y to z. So if you have a measure of dissimilarity that fulfills these constraints, then it is a distance, but we can do clustering with other kinds of measures of difference or dissimilarity or proximity and similarity that are not quite distances. But this is something that we need in all cases when we are doing clustering, because in order to group together examples that are more similar and retain in different groups examples that are less similar to one another, we need to have some measure of this similarity, distance, proximity, whatever we may call it. But for hierarchical clustering, we need an additional level here. So we need this linkage, which is a measure of similarity or dissimilarity between clusters. So in order to get this, we need to find some way of measuring this not only between individuals, between examples, but also between clusters. So when looking at examples, there are some used measures of distance between examples. We can have, for example, the Euclidean distance. This is very often used. We can have the square of the distance. So Euclidean distance is the square root of the square of the difference between the coordinates, for example. And in this case, we don't do the square root, so we have the square of the Euclidean distance. We have Manhattan distance, which instead of doing this power of 2 is just the modulus of the differences in the coordinates. And then we have other variants. For example, Mahalanobis normalizes the distance by the covariance between the different directions, so we can adjust automatically by this variance. Hamming distance can be used, for example, to compare strings, because it's just summing or counting the number of distances between the two vectors. So if you have vectors of Boolean values or strings or something like that, you can use this to measure differences. So there are many different ways of measuring distance between examples, depending on the problem that you have. But then we can extend this to linkage, which is the measure of distances between clusters. And now we have different linkage criteria, which depend on how we extend the measure of these distances between examples to measure distances between clusters. So one example would be to use single linkage. Single linkage takes the distance between two clusters, J and K here, as being the minimum distance between elements of J and elements of K. So we take the two closest examples in the two clusters, and this will stand as the distance between the two clusters. With complete linkage, we do the same thing approximately, but we take the maximum distance instead of the minimum distance. So we consider all the pairs of distances between examples in one cluster and the other cluster, and we take the largest one to stand for the distance between the two clusters. Centroid linkage is the distance between the mean points, the centroids of the clusters. Then we have other examples. Average linkage takes the mean of the distances between all pairs from one cluster to the other. The median linkage takes the median instead of the mean. Word linkage is a bit different. It does not tell us exactly the distance between the clusters, but it also serves as a linkage because we minimize the sum of the squared errors within each cluster, and so this way we can assign points to one cluster or the other in order to minimize this sum of square errors. So it also gives us implicitly a measure of how similar or dissimilar these clusters are. So basically for hierarchical clustering, we need to be able to compare examples so that when we are doing the clusters, we can measure which examples are closer to other examples, but we need an extension of that to compare clusters too, and that's called linkage, and we have different ways of using distance measures between examples to produce these linkage measures. One advantage of hierarchical clustering is that we do not need to assume a number of clusters. And then we get a hierarchical organization of clusters within clusters that hopefully correspond to some aspect of the data that we want to capture. For example, if our data is about species, we can see the relations between the species, which ones are closer together, and get, for example, a phylogenetic tree. The disadvantages are that usually we cannot look at all the possible combinations of clusters of clusters. So in general, hierarchical clustering algorithms take a single pass, aggregating or splitting apart the clusters. And if they make a mistake at one point, then everything that follows will propagate that error. So unless there is some hierarchical structure in the nature of the data, this may be completely wrong, and may even lead us to confusing results or to something that is misleading. So we should use hierarchical clustering only when there is some reason to think that organizing data in this way will be meaningful and it will be informative. So we can consider two types of hierarchical clustering algorithms. Agglomerative clustering works bottom up, starting with clusters of individual examples, then joining the best two or the closest ones according to the linkage measure, and then repeat that until all are joined. This tends to be the complexity for this algorithm tends to grow with the cube of the number of examples, but it can be very much improved if we place constraints on the linkage. We are going to look at some examples of that. Divisive clustering works top down. You start with all examples in a single cluster and then split that cluster, and then pick another cluster to split it again, and repeat until all examples are separated or until you reach the number of clusters that you want. So you can stop at any time and you have the complete tree up to that level. This is generally the complexity increases with the quadratically with the number of examples, and you also need an additional clustering algorithm for the splitting, but it can be very good if you have a fast algorithm for clustering, and if you only want, especially if you only want a few levels of the tree from the top, because then you only need a few iterations and you stop with the number of clusters that you want. So let's see how agglomerative clustering works. You start with singleton clusters, that is, each example is its own cluster, and then you aggregate, you join using the linkage function those that are closest together. And we keep doing this, and eventually we start grouping clusters and then clusters of clusters and so on. And as we rise in the tree, we start grouping things into larger groups. So if we represent this as a dendrogram, so with this representation, we see these were the first clusters being generated, but then we start grouping clusters of clusters and grow to larger groups at each step. Now we have as the result this hierarchy of clusters, but if we want a partitional clustering, we just need to select a level on this tree, on this dendrogram, and cut the links between the clusters at that level. For example, suppose that we want to split this into two clusters. We can take this highest level of the tree, cut here, and this will result in cutting this link between these two clusters, and we separate these two. So we can transform the hierarchical clustering in a partitional clustering by cutting this link and aggregating everything else in their respective branches of the tree. We can go down more in this level. If we cut here, then we have three clusters. So we are cutting these two links at the highest level, and it results in three clusters, four clusters if we cut the next one, five clusters, and so on. So we can go down the tree as far as we want in order to get the number of clusters that we want. Agglomerative clustering is generally not good for large data sets because of the complexity being on the order of the cube of the number of examples. But we can improve that if we add some connectivity constraints. And also connectivity constraints can be useful if we do not want clustering to aggregate solely by distance. So if we do not want these points to be in the same cluster as these points here, just because they are close together, and we want clustering to follow this pattern here on this spiral, we can do that with connectivity constraints. And this is how it works, and it's easy to do in scikit-learn. So connectivity constraints define a graph of connections between examples, and only clusters that are connected by examples in that graph can be joined. So this forces clustering to respect this graph where we specify the connections, and it also speeds up computation because the algorithm doesn't need to consider all pairs of examples, only those that have connections along the graph. So with scikit-learn, we can use this agglomerative clustering class, and this takes in a matrix for connectivity, which is a matrix of n by n examples. N is the number of examples that we have, and it's a matrix with 0 everywhere there is no connection between examples, and the one where the examples are connected. This is also a sparse matrix. This is a special kind of matrix that NumPy can represent that is greatly compressed. So even though this matrix is potentially very large because it's n by n examples, since most of the entries are 0, it doesn't take too much space in memory. And we can easily create this matrix by using this k-neighbors graph, which takes the nearest neighbors, in this case the 10 nearest neighbors for each point, and creates the matrix connecting each point only to its 10 nearest neighbors. So here we add this as the connectivity matrix to agglomerative clustering. We specify the number of clusters because this will start with all examples in the individual clusters, but then we'll aggregate them, and when it reaches the number of clusters we specify, it will stop. And now we can fit our data, and the results will look like this. Instead of having these results where we have clusters formed blindly reaching out over space, since we create a connectivity matrix joining each point to its closest 10 neighbors, then the graph will follow this strip here, and it will not cross over these intervals. So when we do the clustering with that connectivity matrix, we get this different set of clusters that no longer jump through these gaps here. So agglomerative clustering, you can specify the number of clusters, the affinity, which is the measure of distance between examples, the linkage, which is the measure of distance between different clusters. So basically you can use complete, average, or word linkage by specifying here. And then after fitting, you can find the labels for all your samples, and also the children tell you how the clusters are related. So which cluster is a child of which cluster. And this can allow you to reconstruct the tree of the hierarchical cluster. So differences between linkages will depend on the data that you have and the kind of results that you want, but in general, complete linkage tends to favor larger clusters. So in this case, we get these larger clusters grab more examples. Average linkage solves that partially, but in general, word linkage works best, but you need to use Euclidean distances for word linkage to work. But this tends to capture better the pattern in the data when you have clusters of different sizes. Okay, another approach to hierarchical clustering is to start from the top. So we start with a single cluster, all the examples join together in a single cluster, and now we're going to split the cluster. We have one criteria for selecting a cluster, for example, the one with the largest number of examples or the lowest score, something like that. We split it in the case of bisecting k-means, we split it using k-means with a k equals 2, and then we repeat this until we get the desired number of clusters. For example, in this case, we start by splitting this single cluster, then we split always on the largest cluster, that is, on the cluster that has the largest number of elements, and now we keep splitting and splitting until everything is separated into individual clusters. So this would be an example of bisecting k-means. In this case, the criteria is to always pick the cluster with the largest number of elements, but you can have different criteria. And we proceed iteratively by splitting the clusters into subclusters. We can store the relations between the clusters, and now we have this tree again. But in this case, in the case of agglomerative clustering, we start building the tree from the bottom up. So individual clusters, aggregate them until we reach this final edge here. In divisive clustering, or in particular the case of bisecting k-means, we start from the top, everything is on the same cluster, and then we split and go down. But you can, at any point, turn this into a partitional cluster by just specifying where you want to cut. So an exhaustive search will be quadratic on the order of examples, and this requires clustering at each step, so you need an additional clustering algorithm. But especially if you want a few large clusters, or if you have a fast clustering algorithm for each step, this can be very efficient, because you can stop only after a few iterations if it's enough for you, or if the auxiliary clustering algorithm is fast, you can quickly iterate through all these levels. So let's see another application of clustering, and we're going to use agglomerative clustering for this because of the connectivity constraints. But one possible application of clustering is, instead of clustering examples, we cluster features, and using that we can reduce the number of dimensions in our data. So the basic idea is this. Usually when we do clustering, we have each feature on a column in our matrix, and each example is a different row. So now we are going to group examples together according to the similarity or dissimilarity by looking at their features. But imagine that we transpose this matrix and we put the features on the rows and the examples on the columns. So basically, we are now treating our examples as being those vectors of the values of each feature over all our data set. So this would be the first example in this transposed matrix, would be a vector that has the value of feature 1 on example 1, of feature 1 on example 2, and so forth. So this would be one vector that will serve as example, and this would be another vector that will serve as another example, and this is for the second feature, and so on. Now, if we aggregate, if we cluster these rows like this, we are going to find those features that are more alike when we consider the whole set of data that we have. So we can actually group features together by their similarity. And this is what feature clustering does. And we can then reduce the dimensionality of our data by, for example, averaging all the features that are similar and considering that to be just a single feature. So let's see an example with the handwritten digits dataset. This is a dataset that you have available in scikit-learn, and it represents these handwritten digits with small matrices of 8 by 8 pixels. So basically we have 64 features for each digit, which is the array of 8 by 8 pixels we have here. Each feature varies from 0 to 1, which are the values of intensities that we can get here. And we can convert these, we have these examples, 1797. We can convert these examples of 64 features each, so 64 columns, but we can transpose that matrix and consider 64 examples, each one containing 1797 features. So now our examples are each individual pixel, for example, this pixel in the corner here, and the vector that describes this pixel is the intensity of this pixel on all the examples in our data set. So this will be 1797 features for this particular pixel, and then the same for the other pixel, and so on for all 64 pixels. So this is the original data. We can read it like this. You have this, in scikit-learn, you have this datasets module. So you can do the load digits from there. This is a standard data set that you can use as a demo. You can get the digits. So this object has the labels, the images, and so on. You can get the images from these digits. This will give you a matrix with all these different images. And now we can reshape this so that we have as many rows as we have images, and as many columns as necessary to fill in all the data. So in this case, it will be 64 columns. So this would be our data matrix, 1797 rows, one for each image, 64 columns, one for each pixel. Now we can create a connectivity graph to cluster only the pixels that are adjacent to each other. So we don't want to put in the same cluster a pixel on this corner and a pixel over here if there is nothing connecting them. So we're going to create a connectivity graph for all these 64 features by considering the pixels that are adjacent to one another to be connected to one another. This is also simple to do. You have this grid to graph function in the feature extraction module for the images. So you can use this grid to graph specifying the height and width of some image. So in this case, it's just the sizes of the images, and this will create the connectivity matrix specifying which pixels are adjacent to each other. So now we're going to do agglomerative clustering on this data, but to cluster the features. We could do the transposition ourselves and then use agglomerative clustering, but we have this feature agglomeration class that uses agglomerative clustering for features, so we don't need to do that manually. We just create this object, we fit our data, and what it's doing is fitting the features, clustering the features and not the examples. So now we can get the reduced data by transforming our original data, and what this transformation does is it aggregates those features that fall into the same clusters and averages the values for those features. So now we have a reduced data set that will only have this number of clusters, 16. So it will only have 16 features instead of 64. We can also we can do the inverse by going back to the 64 features again, but in this case by duplicating the values we have in the reduced data set. Okay, so let's look at how this looks like in the images because it's easier to understand. These are the clusters that were computed. So the result of this fit was to produce 16 clusters by agglomerating, by clustering together the pixels according to this connectivity. So the pixels were clustered together by looking at how similar they are when we consider the whole set of examples, and with the constraint that we must group together pixels that are adjacent. So, for example, this region here is composed of pixels that seem to be very similar over all the examples. And this makes sense because these pixels tend to be mostly black because they fall outside the region where the numbers are written. And then we have other regions here. For example, on this side, we also have a large number of similar pixels, probably for the same reason. And then we have different clusters here inside because the numbers are changing and some of these features apparently are important. But the result is that we clustered the 64 different pixels into 16 groups of similar pixels when considering the whole data set. So now we can reduce the data. This is the original data. This is the data reduced and then restored. So we still have 64 pixels here, but now the clusters of pixels that are similar will have the same value, which is the average of the pixels in the original data. So this will be the value for this region here, another region here, and so on. But we can actually use only the 16 different values, and so we can convert our data into a representation that only has 16 features. For example, representing with images of 4 by 4 pixels. Note that now these images do not look like digits because we are completely scrambling everything. We are taking, for example, all of these pixels to be just one single pixel. These pixels here are another pixel, and so on. But it's still possible to see that the zeros have one shape that is not quite the same as the ones and different from the twos and so on. So this agglomeration of the features is still capturing the differences between the digits. It simplified the representation by giving us fewer features, but it agglomerated them, joined them together according to their similarity, so we are not losing that much information when we reduce the dimensionality in this way. So to sum up, hierarchical clustering is for generating nested clusters, clusters within clusters, but then we can convert that into a partitional clustering by cutting at some point. So these examples that we saw with agglomerative clustering, we specify a number of clusters and it stops the agglomeration at that point. We need both to measure similarity or distance between examples and also between clusters, and that is called linkage. The distance measures between clusters is linkage. We can do hierarchical clustering from the bottom by agglomerating individual examples and then smaller clusters into larger clusters, or from the top by joining everything together first and then splitting the groups, for example, with k-means in the case of bisecting k-means. There are different effects of different linkage options, so you need to think about what would be best for your particular data. And also another application of clustering that we saw here today using agglomerative clustering is to cluster features in order to reduce dimensionality of some representation. Okay, so you can take a look at the clustering documentation on scikit-learn. There are also some demonstrations of different clustering algorithms, and it's a good idea to look at the results, at the graphs, because it gives you an intuitive feeling of what the different algorithms do.